Hey guys, tonight we're taking a journey that's going to absolutely shatter everything you think you know about reality. We're talking about Earth, our solar system, and the mind-bending cosmos beyond. And trust me, by the end of this, you'll never look up at the night sky the same way again. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And let me know in the comments where you're tuning in from and what time it is for you. It's always fascinating to see who's joining us from around the world. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's cosmic journey together. You think you live on a solid, stable planet, spinning peacefully through space. You couldn't be more wrong. Right now, as you sit there listening to this, you're hurtling through the universe at speeds that would make a fighter jet look like it's standing still. Earth isn't just rotating. It's screaming through space at over 67,000 miles per hour around the Sunday. But that's not even the half of it. Our entire solar system is racing around the center of the Milky Way galaxy at 514,000 miles per hour. And the Milky Way itself is flying through space at over 1.3 million miles per hour toward the Andromeda galaxy. So while you think you're sitting still, you're actually on a cosmic roller coaster moving at combined speeds of nearly 2 million miles per hour through the void. In the time it takes you to blink, you've traveled about 500 miles through space. In the time it takes to watch this video, you'll have journeyed hundreds of thousands of miles on Spaceship Earth, and you didn't even feel it. But that's just the beginning of how wrong our intuitions are about the place we call home. Let's start with some facts about Earth that will make you question everything you thought you knew about our planet. Did you know that Earth isn't actually round? I know, flat earthers aren't right either. But the truth is, our planet is what scientists call an oblate spheroid. It's basically a squished ball, flattened at the poles and bulging at the equator. The difference isn't small either. Earth is about 27 miles wider at the equator than it is from pole to pole. That's because the planet is spinning so fast that centrifugal force literally stretches it outward at the middle. And speaking of spinning, here's something that'll blow your mind. The Earth's rotation is actually slowing down. Every day is getting longer, but by an incredibly tiny amount, about 1.7 milliseconds every century. That might not sound like much, but it adds up. When Earth first formed 4.5 billion years ago, a day was only about 6 hours long. The moon, which was much closer back then, was pulling on Earth's tides so strongly that it acted like a brake, gradually slowing our planet's rotation. Here's where it gets really weird. The moon is still doing this today, and it's actually moving away from us at about 1.5 inches per year. That's roughly the same rate your fingernails grow. So, every year, our days get a tiny bit longer, and the moon drifts a little further away. In about 50 billion years, if the sun doesn't destroy us first, Earth days will be 47 of our current days long, and the moon will appear much smaller in the sky. But let's talk about something even more mind-bending. The ground beneath your feet right now isn't as solid as you think. Earth's crust, the part we live on, is incredibly thin compared to the rest of the planet. If Earth were the size of an apple, the crust would be thinner than the apple's skin. We're literally living on a paper-thin shell floating on an ocean of molten rock, and that molten rock is moving. The entire surface of our planet is in constant motion, riding on massive tectonic plates that drift around like puzzle pieces on a sea of magma. Right now, North America is moving away from Europe at about the same rate your fingernails grow. In 50 million years, Los Angeles will be where San Francisco is today. The Atlantic Ocean is getting wider every year, while the Pacific is shrinking. Here's something that might keep you up at night. These tectonic plates sometimes get stuck against each other, building up enormous pressure. When they finally slip, we get earthquakes. And some of the earthquakes waiting to happen are absolutely terrifying. The Cascadia subduction zone off the Pacific Northwest coast is overdue for a massive earthquake that could be magnitude 9 or higher. When it happens, it'll create tsunamis that could reach 100 feet high and devastate the entire Pacific Rim. But earthquakes aren't even the most dangerous thing our planet throws at us. Did you know that right now, there are about 1,500 active volcanoes around the world? And that's just the ones we know about. There are thousands more under the ocean that we haven't even discovered yet. Some of these underwater volcanoes are absolutely massive. The largest volcano on Earth isn't actually on land at all. It's Tamu Massif, an underwater mountain in the Pacific Ocean that covers an area the size of New Mexico. And then there are supervolcanoes. These are volcanic systems so large that when they erupt, they can change the climate of the entire planet. The most famous one is probably Yellowstone, which sits on top of a magma chamber that's 55 miles long, 20 miles wide, and 5 miles deep. When Yellowstone last erupted 640,000 years ago, it ejected 240 cubic miles of material into the atmosphere. That's enough to bury the entire state of Texas under 3 feet of ash. If Yellowstone erupted today, it would be a global catastrophe. The ash cloud would block out the sun, causing global temperatures to drop by several degrees and triggering what scientists call a volcanic winter. Crops would fail worldwide, and billions of people could starve. And here's the kicker. Yellowstone erupts roughly every 600,000 to 800,000 years. It's been 640,000 years since the last eruption. We're not overdue yet, but we're getting close to the danger zone. But let's move on from the terrifying stuff and talk about some of the more amazing aspects of our planet. Did you know that Earth has more than one moon? Well, sort of. In addition to our big moon, Earth regularly captures small asteroids that orbit us for a few months or years before flying away again. These are called temporary moons or quasi-satellites. Right now, we have at least one confirmed temporary moon called 2020 CD3, which is about the size of a car. And our main moon is far more important to life on Earth than most people realize. Without the moon, our planet would be a very different place. The moon's gravity doesn't just cause tides in our oceans. It also stabilizes Earth's axial tilt. Without the moon, our planet would wobble chaotically, causing extreme climate changes that would make complex life nearly impossible. The moon also slows down Earth's rotation, as we talked about earlier. Without it, our days would only be about 8 hours long, and the resulting high-speed winds would create permanent global storms. So in a very real sense, we owe our existence to a cosmic accident that happened 4.5 billion years ago, when a Mars-sized object smashed into the early Earth and created the moon from the debris. Speaking of cosmic accidents, here's something that might surprise you. Earth's atmosphere is actually incredibly thin, If you could drive a car straight up at highway speeds, you'd reach the edge of space in about an hour. The vast majority of our atmosphere, about 99% of it, is contained within just 20 miles of the surface. That's a smaller distance than many people commute to work every day. And that thin layer of air is the only thing protecting us from the deadly radiation and vacuum of space. But it's not just protection. It's also a massive recycling system. Every breath you take contains atoms that have been breathed by countless other living things throughout history. The oxygen in your lungs right now might have been exhaled by a dinosaur 100 million years ago, or by Julius Caesar, or by your great-grandmother. Water works the same way. The water you drink today has been cycling through the Earth system for billions of years. It's been inside other people, animals, plants, clouds, oceans, and underground rivers. Some of the water in your body might have once been part of a comet that crashed into Earth billions of years ago. You're literally made of stardust and ancient cosmic ice. And speaking of water, here's something incredible. Despite the fact that about 71% of Earth's surface is covered by water, almost all of it is salt water that we can't drink. If all the water on Earth were contained in a gallon jug, the fresh water would only fill about 1 tablespoon. And most of that fresh water is locked up in ice caps and glaciers. The amount of liquid fresh water available to all life on Earth would barely fill a teaspoon. This makes Earth's hydrological cycle one of the most important and amazing systems in the universe. Every day, the sun evaporates about 280 cubic miles of water from Earth's surface. That water rises into the atmosphere, forms clouds, and eventually falls back down as rain or snow. This process not only provides the fresh water that life depends on, but it also helps regulate Earth's temperature by moving heat around the planet. But here's where it gets really mind-blowing. The water cycle connects everything on Earth in ways that most people never think about. The rain that falls in your backyard might have evaporated from the Amazon rainforest last week. The snow on a mountain in Colorado could end up in the Gulf of Mexico 6 months later. The cloud you see overhead might contain water that was once part of the Indian Ocean. And this is where we need to talk about just how interconnected and fragile Earth systems really are. Our planet isn't just a big rock with some water and air stuck to it. It's an incredibly complex, self-regulating system where everything affects everything else. Scientists call this the Gaia hypothesis, the idea that Earth functions almost like a single living organism. For example, the Amazon rainforest doesn't just affect the local climate in South America. It actually influences weather patterns around the entire world. The trees in the Amazon release water vapor and chemicals that help form clouds, not just locally but thousands of miles away. If the Amazon were completely destroyed, it would change rainfall patterns across the globe and could trigger a collapse of the entire climate system. The same goes for the ocean currents. The Gulf Stream, which carries warm water from the Caribbean up the east coast of North America and across to Europe, is part of a global circulation system that scientists call the ocean conveyor belt. This system moves heat around the planet and helps regulate global climate. If it's shut down, which some scientists think could happen due to climate change, Europe could actually become much colder even as the rest of the planet warms up. These kinds of connections exist everywhere on Earth. The plants and animals in any ecosystem are connected not just to each other, but to the soil, the water, the air, and even to ecosystems thousands of miles away. A volcanic eruption in Indonesia can affect the growth of trees in Alaska. A drought in Africa can influence the formation of hurricanes in the Atlantic. Everything is connected in ways that we're only just beginning to understand. And that brings us to one of the most sobering facts about our planet. Despite all our technology and scientific knowledge, we still don't really understand how Earth works. We know a lot of individual pieces, but the system as a whole is so complex that it's almost impossible to predict what will happen when we change things. Take climate change, for example. We know that adding carbon dioxide to the atmosphere traps more heat. But the exact consequences of that warming are incredibly difficult to predict because there are so many feedback loops and interconnected systems. Will warming cause more clouds, which would reflect sunlight and cool the planet? Or will it cause less clouds, which would accelerate the warming? Will melting permafrost release enough methane to trigger runaway global warming? Will changes in ocean circulation shut down the Gulf Stream? These are questions that could determine the future of human civilization. And we honestly don't know the answers. We're running a massive experiment on the only planet we have, and we won't know the results until it's too late to change course. But let's step back from the scary stuff and talk about some of the more amazing aspects of Earth's climate and weather systems. Did you know that Earth's weather is powered by an absolutely incredible amount of energy? Every day, the sun delivers about 173,000 terawatts of energy to Earth. That's more than 10,000 times the total energy consumption of all human civilization. Most of that energy goes into heating the surface and driving the water cycle. But even a tiny fraction of it creates weather phenomena that are almost incomprehensibly powerful. A single thunderstorm releases as much energy as a 20-kiloton nuclear bomb. A hurricane can release the energy equivalent of 200 times the world's total electrical generating capacity. And the Earth experiences about 2,000 thunderstorms and 80 tropical cyclones every year. Lightning alone is one of the most amazing phenomena on our planet. Every second, there are about 50 lightning strikes happening somewhere on Earth. That's more than 4 million lightning strikes per day. Each lightning bolt is hotter than the surface of the sun, reaching temperatures of about 54,000 degrees Fahrenheit. The electrical current in a lightning strike can be up to 30,000 amperes, which is enough to power a small town for a month. And here's something really weird about lightning. We still don't completely understand how it works. We know that ice particles in storm clouds build up electrical charge through collisions. But the exact mechanism that creates the massive electrical potential difference needed for lightning is still a mystery. Some scientists think cosmic rays from space might play a role in triggering lightning strikes. Speaking of cosmic rays, they're constantly raining down on Earth from space. These are high-energy particles, mostly protons, that have been accelerated to incredible speeds by exploding stars, black holes, and other cosmic phenomena. Every second, hundreds of cosmic ray particles pass through your body. Most of them are harmless, but occasionally one will hit a computer chip and cause what's called a soft error, flipping a bit of data from 0 to 1, or vice versa. This actually happens more often than you might think. Cosmic rays are responsible for a small but measurable percentage of computer crashes and electronic malfunctions. In fact, as we build more sensitive electronics and send them higher into the atmosphere and into space, cosmic ray interference becomes a bigger and bigger problem. But cosmic rays also do something amazing. When they hit Earth's atmosphere, they create showers of subatomic particles that rain down on the surface. Some of these particles are muons, which are like heavy electrons that can pass through solid matter. Right now, several muons are passing through your body every second. You can't feel them, but they're there. Ghostly messengers from the cosmic particle accelerators scattered throughout the universe. And speaking of things from space hitting Earth, let's talk about meteorites. Every day, about 100 tons of cosmic material falls to Earth. Most of it is tiny dust particles that burn up in the atmosphere. But occasionally, larger chunks make it to the surface. Scientists estimate that about 17,000 meteorites, larger than 100 grams, hit Earth every year. But most of them fall in the ocean or in remote areas where no one finds them. The meteorites we do find tell us incredible stories about the history of the solar system. Some of them are older than Earth itself, formed in the early days of the solar system 4.6 billion years ago. Others come from the Moon or Mars, blasted off those worlds by massive asteroid impacts, and then wandering through space for millions of years before landing here. One of the most amazing things about meteorites is that they've brought us samples of other worlds without us having to go there. We've learned more about the composition of Mars from Martian meteorites found on Earth than from all of our Mars missions combined. And some meteorites contain organic compounds, the building blocks of life, suggesting that the ingredients for life might be common throughout the universe. In fact, some scientists think that life on Earth might have originally come from space, delivered by meteorites or comets. This idea is called panspermia, and, while it's still controversial, there's growing evidence that organic compounds can survive the journey through space and the impact with a planet's surface. But let's talk about some of the life that we know is native to Earth, because it's far more amazing than most people realize. Did you know that the vast majority of life on Earth is invisible? Bacteria and other microorganisms make up about 15% of the total biomass on Earth, but they're arguably the most important living things on the planet. These microscopic creatures do most of the heavy lifting when it comes to keeping Earth's systems running. They recycle nutrients, produce oxygen, decompose dead material, and even influence the weather. Some bacteria in the upper atmosphere help form ice crystals in clouds. Others in the soil help plants grow by fixing nitrogen from the air. And in the ocean, tiny bacteria called cyanobacteria produce about half of the oxygen we breathe. The diversity of microbial life is absolutely staggering. Scientists estimate that there might be as many as 1 trillion different species of bacteria on Earth, and we've only identified a tiny fraction of them. Some of these bacteria live in environments that would kill any other form of life. There are bacteria that thrive in boiling water, in acid that would dissolve metal, in salt concentrations that would pickle a human, and even in the cooling water of nuclear reactors. One of the most extreme environments on Earth is the deep ocean floor, where bacteria live around hydrothermal vents in water that's hotter than 750 degrees Fahrenheit, and under pressure that would crush a human instantly. These bacteria don't use sunlight for energy like most life on Earth. Instead, they get their energy from chemical reactions involving hydrogen sulfide and other toxic chemicals spewing from the vents. This discovery revolutionized our understanding of life and where it might exist in the universe. If life can thrive in these extreme conditions on Earth, maybe it could exist on other worlds that we previously thought were too harsh for life. Maybe there are bacteria living in the subsurface oceans of Jupiter's moon Europa, or in the methane lakes of Saturn's moon Titan, or even in the clouds of Venus. But the most mind-blowing thing about life on Earth isn't its diversity, or its extremophile capabilities. It's the fact that all life on Earth is related. Every living thing, from the bacteria in your gut to the largest whale in the ocean, shares a common ancestor that lived billions of years ago. We know this because all life on Earth uses the same basic genetic code and the same fundamental biochemistry. This means that you are literally cousins with every other living thing on the planet. You share about 50% of your DNA with a banana, about 60% with a fruit fly, and about 98.8% with a chimpanzee. But even more amazingly, you share fundamental cellular machinery with bacteria that have been around for billions of years. The fact that all life is related also means that Earth's biosphere is incredibly interconnected. When one species goes extinct, it affects all the other species that depended on it, which affects the species that depended on them, and so on. We're currently in the middle of what scientists call the sixth mass extinction, with species disappearing at a rate that's 100 to 1,000 times faster than the natural background rate. This isn't just sad from an environmental perspective. It's potentially catastrophic for human civilization. The complex web of life that supports our food systems, our climate, and our economy is being unraveled species by species. And because everything is so interconnected, we often don't know which species are critical until they're gone, and the whole system starts to collapse. But let's move on from the somewhat depressing topic of extinction and talk about some of the more amazing facts about Earth's biodiversity. Did you know that we still don't know how many species live on our planet? Scientists have formally described about 1.2 million animal species and about 300,000 plant species. But estimates for the total number of species on Earth range from 8 million to 100 million. Most of the undiscovered species are probably insects, many of them living in tropical rainforests that haven't been thoroughly explored yet. Every year, scientists discover thousands of new species, from tiny beetles in the Amazon to new species of mammals in remote mountains. In 2019, researchers discovered 71 new species in just one expedition to a single mountain in Bolivia. And it's not just remote places where we're finding new species. Scientists regularly discover new species in major cities, in suburban backyards, and even in well-studied environments like coral reefs. This suggests that Earth's biodiversity is even greater than we imagined, and that we've barely scratched the surface of cataloging life on our own planet. One of the most amazing discoveries in recent years is the existence of vast ecosystems in places we never thought life could exist. Deep beneath the ocean floor, sometimes several miles down in solid rock, scientists have found thriving communities of bacteria and other microorganisms. These deep biosphere communities might contain more biomass than all the life on Earth's surface combined. Even more amazingly, some of these deep-dwelling organisms are incredibly old. Some bacteria samples taken from deep underground have been carbon dated to be millions of years old, suggesting that they've been living in isolation for geological time periods. They've been cut off from the surface world since before humans evolved, living off chemical energy in the rocks and reproducing so slowly that some individual bacteria might be thousands of years old. This discovery has huge implications for the search for life on other planets. If life can exist deep underground on Earth, maybe it exists deep underground on Mars, or on the moons of Jupiter and Saturn. Maybe the universe is teeming with life, but most of it is hidden beneath the surfaces of planets and moons where we haven't thought to look. But let's zoom out from Earth and start talking about our solar system, because it's far weirder and more wonderful than most people realize. Let's start with our Sun, which is a pretty average star by cosmic standards, but still an absolutely incredible object. The Sun contains 99.86% of all the mass in our solar system. Jupiter, which is by far the largest planet, has only about 1,000th the mass of the Sun. All the planets, moons, asteroids, and comets combined make up less than 0.2% of the solar system's total mass. We're basically living in the gravitational empire of a single massive ball of nuclear fire, and that nuclear fire is incredible. Every second, the Sun converts about 600 million tons of hydrogen into helium through nuclear fusion. In the process, it loses about 4 million tons of mass, which is converted directly into energy. According to Einstein's famous equation, E equals mc squared. That's equivalent to exploding 100 billion tons of TNT every single second. The core of the Sun, where this fusion happens, reaches temperatures of about 27 million degrees Fahrenheit and pressures 250 billion times greater than Earth's atmospheric pressure. Under these extreme conditions, hydrogen nuclei are crushed together so hard that they overcome their natural electrical repulsion and fuse into helium, releasing tremendous amounts of energy in the process. But here's something weird. The energy produced in the Sun's core doesn't reach us immediately. It actually takes tens of thousands of years for that energy to work its way from the core to the surface of the Sun, bouncing around and being absorbed and re-emitted countless times. The sunlight hitting your face right now was actually created when the last ice age was ending on Earth. Once that energy reaches the Sun's surface, it travels to Earth at the speed of light, taking about 8 minutes and 20 seconds to make the journey. This means that the Sun you see in the sky is actually the Sun as it was 8 minutes and 20 seconds ago. If the Sun suddenly disappeared right now, we wouldn't know about it for more than 8 minutes. And the Sun is constantly changing. Its surface is covered with massive magnetic storms called solar flares and coronal mass ejections that can release more energy than all the nuclear weapons on Earth combined. These solar storms create the beautiful auroras we see near Earth's poles. But they can also disrupt satellite communications, damage power grids, and pose a radiation hazard to astronauts. In 1859, a massive solar storm called the Carrington Event caused telegraph systems around the world to fail. Some telegraph operators received electric shocks, telegraph paper caught fire, and some telegraph systems continued to work even after they were unplugged from their power sources, running entirely on the electrical current induced by the solar storm. If a similar event happened today, it could cause trillions of dollars in damage to our electronic infrastructure. But solar storms aren't the only way the Sun affects Earth. The Sun's output actually varies slightly on an 11-year cycle, and these variations can influence Earth's climate. During periods of low solar activity, called solar minimums, Earth tends to be slightly cooler. The most famous example is the Maunder minimum from 1645 to 1715, which coincided with the Little Ice Age in Europe. The Sun is also slowly getting brighter as it ages. Over the next billion years, the Sun's energy output will increase by about 10%, which will gradually make Earth too hot to support life. Long before that happens, probably in about 5 billion years, the Sun will start running out of hydrogen fuel in its core and will begin to expand into a red giant star. It will eventually become so large that it will swallow Mercury and Venus, and possibly Earth as well. But let's not worry about that now, and instead talk about the planets in our solar system, starting with Mercury. The closest planet to the Sunday, Mercury, is a world of extremes. During the day, temperatures on Mercury can reach 800 degrees Fahrenheit, hot enough to melt lead. But at night, temperatures can drop to minus 300 degrees Fahrenheit, colder than the surface of Pluto. This extreme temperature variation happens because Mercury has almost no atmosphere to trap heat, and because its day is very long compared to its year. Mercury rotates so slowly that one day on Mercury lasts about 59 Earth days. But it orbits the Sun so quickly that its year is only 88 Earth days long. This means that on Mercury, a day is longer than a year. Mercury is also a very dense planet, with a huge iron core that makes up about 75% of its radius. Scientists think this happened because Mercury formed much closer to the Sun than it is now, and the intense solar wind blew away most of its rocky outer layers, leaving behind a mostly metal world. Venus, the next planet out, is often called Earth's twin because it's about the same size and mass as our planet. But Venus is actually a hellish world that shows what can happen when a planet's climate goes completely out of control. The surface temperature on Venus is about 900 degrees Fahrenheit, hot enough to melt copper, and the atmospheric pressure is 90 times greater than Earth's, equivalent to being under 3,000 feet of water. The reason Venus is so hot is because of a runaway greenhouse effect. Venus's atmosphere is about 96% carbon dioxide, with clouds made of sulfuric acid. These thick clouds trap heat so effectively that Venus is actually hotter than Mercury, even though it's much farther from the Sunday. The surface pressure is so great that it would crush a human instantly, and the sulfuric acid rain would dissolve any spacecraft that tried to land there. Venus also rotates backwards compared to most other planets, and it rotates so slowly that a day on Venus lasts 243 Earth days. This means that on Venus, a day is longer than a year, just like on Mercury. Scientists aren't sure why Venus rotates backwards, but they think it might have been hit by a massive asteroid early in its history that reversed its rotation. Some scientists think Venus might have been a lot like Earth billions of years ago, with oceans and possibly even life. But something went wrong with its climate, possibly triggered by massive volcanic eruptions, and all the water evaporated into space. Venus is a cautionary tale about what happens when a planet's climate system breaks down completely. Mars, our other neighboring planet, tells a different but equally fascinating story. Mars today is a cold, dry desert world with an atmosphere so thin that liquid water can't exist on most of its surface. But there's overwhelming evidence that Mars was once a much warmer, wetter world with flowing rivers, vast lakes, and possibly even oceans. We can see the evidence of this ancient water everywhere on Mars. There are dried-up riverbeds, lake beds, and what looks like ancient shorelines. Some of these features are billions of years old, suggesting that Mars had a thick atmosphere and liquid water on its surface for hundreds of millions of years, possibly long enough for life to evolve. The big question is what happened to Mars's atmosphere and water. The planet is much smaller than Earth, So it has weaker gravity that can't hold onto a thick atmosphere as well. Mars also doesn't have a strong magnetic field like Earth does. So the solar wind can strip away atmospheric particles directly. Over billions of years, most of Mars's atmosphere escaped into space, leaving behind the thin, cold world we see today. But Mars still has water, lots of it, frozen in its polar ice caps and buried underground as permafrost. Recent discoveries by Mars rovers and orbiters have found evidence of liquid water existing seasonally in some locations, and there might be vast underground aquifers of liquid water beneath the surface. This is incredibly exciting, because wherever we find liquid water on Earth, we find life. If there's liquid water on Mars, there might be life there too. Probably in the form of bacteria or other microorganisms living underground. Several Mars missions are specifically looking for signs of past or present life. And some scientists think we might have an answer within the next decade or two. Mars also has some of the most extreme geological features in the solar system. Olympus Mons, the largest volcano on Mars, is about 16 miles high and 370 miles across at its base. That's almost 3 times taller than Mount Everest and roughly the size of the state of Arizona. The Valles Marineris Canyon system is over 2,500 miles long, 125 miles wide, and up to 4 miles deep. If it were on Earth, it would stretch from New York to Los Angeles. These massive features exist because Mars doesn't have plate tectonics like Earth does. On Earth, the continents are constantly moving. So volcanoes don't stay in one place long enough to grow to enormous sizes. But on Mars, a volcano can sit over a hot spot in the mantle for billions of years, growing larger and larger with each eruption. Moving beyond Mars, we come to the asteroid belt, a region of space between Mars and Jupiter that contains hundreds of thousands of rocky objects left over from the formation of the solar system. The largest asteroid, Ceres, is about 590 miles across and is actually classified as a dwarf planet. It's so large that it has a spherical shape and might even have a subsurface ocean beneath its icy crust. Most asteroids are much smaller, ranging from car-sized chunks of rock to boulders the size of mountains. Despite what you might see in science fiction movies, the asteroid belt isn't densely packed with rocks. The average distance between asteroids is about 600,000 miles, so spacecraft can fly through the asteroid belt without much risk of collision. But some asteroids do pose a threat to Earth. There are currently about 2,000 known near-Earth asteroids larger than half a mile across, and astronomers discover new ones all the time. An asteroid impact was almost certainly responsible for the extinction of the dinosaurs 66 million years ago, and a similar impact today would be catastrophic for human civilization. The asteroid that killed the dinosaurs was probably about 6 miles across and hit Earth with the energy of billions of nuclear bombs. It created a crater 100 miles across in what is now Mexico and threw so much debris into the atmosphere that it blocked out the sun for months, causing a global winter that killed most large animals on Earth. Fortunately, astronomers are now tracking potentially dangerous asteroids and developing technologies to deflect them if necessary. In 2022, NASA successfully crashed a spacecraft into an asteroid called Dimorphos and changed its orbit, proving that we can potentially protect Earth from asteroid impacts if we see them coming far enough in advance. Beyond the asteroid belt lies Jupiter, the giant of our solar system. Jupiter is more massive than all the other planets combined, and it's so large that if you could hollow it out, you could fit all the other planets inside it with room to spare. Jupiter is what's called a gas giant, made mostly of hydrogen and helium with no solid surface to land on. Jupiter's most famous feature is the Great Red Spot, a massive storm that has been raging for at least 350 years, and possibly much longer. This storm is larger than Earth and has winds that reach 400 miles per hour. The fact that it has persisted for centuries shows just how different weather is on a gas giant compared to a rocky planet like Earth. Jupiter has at least 79 known moons, 4 of which are large enough to be considered worlds in their own right. Io is the most volcanically active body in the solar system, with sulfur volcanoes constantly erupting and painting its surface in bright yellows and reds. Europa has a smooth, icy surface that covers a subsurface ocean containing more water than all of Earth's oceans combined. Ganymede is the largest moon in the solar system, bigger than the planet Mercury, and it's the only moon known to have its own magnetic field. Callisto is heavily cratered and might also have a subsurface ocean. All 4 of these moons were discovered by Galileo in 1610, and they played a crucial role in proving that not everything in the universe orbits Earth. Europa is particularly interesting to astrobiologists because its subsurface ocean is kept liquid by tidal heating from Jupiter's gravity. The ice shell is probably only 10 to 20 miles thick, and there might be hydrothermal vents on the ocean floor, similar to the ones that support life in Earth's deep oceans. Some scientists think Europa is one of the most likely places in the solar system to find extraterrestrial life. Jupiter also acts as a kind of cosmic vacuum cleaner, using its powerful gravity to capture or deflect comets and asteroids that might otherwise hit the inner planets. In 1994, astronomers watched as comet Shoemaker-Levy 9 broke apart and crashed into Jupiter in a spectacular series of impacts. Each impact released more energy than all the nuclear weapons on Earth combined, creating dark spots in Jupiter's atmosphere that were larger than Earth. Without Jupiter's protection, Earth would be hit by large asteroids and comets much more frequently, making it much harder for complex life to evolve and survive. In a very real sense, we owe our existence not just to our position in the habitable zone, but also to Jupiter's role as our cosmic bodyguard. Saturn, the next planet out, is famous for its spectacular ring system, but it's also a fascinating world in its own right. Saturn is even less dense than Jupiter, made mostly of hydrogen and helium, and it's actually less dense than water. If you could find an ocean large enough, Saturn would float. Saturn's rings are made of billions of particles of ice and rock, ranging in size from tiny grains to house-sized boulders. The rings are incredibly thin, only about 30 feet thick in most places, but they extend outward from the planet for about 175,000 miles. No one knows exactly how the rings formed, but they might be the remains of a moon that was torn apart by Saturn's gravity, or they might be leftover material from the formation of the solar system. Saturn has at least 82 known moons, including Titan, which is larger than Mercury, and has a thick atmosphere and lakes of liquid methane and ethane on its surface. Titan is the only other body in the solar system besides Earth that has stable bodies of liquid on its surface, although those liquids are hydrocarbons rather than water. Enceladus, another of Saturn's moons, is one of the most exciting destinations for astrobiologists. This small, icy moon has geysers of water vapor and ice particles erupting from its south polar region, indicating that it has a subsurface ocean. The Cassini spacecraft flew through these geysers and detected organic compounds, suggesting that Enceladus might have all the ingredients necessary for life. The outer two planets, Uranus and Neptune, are ice giants made mostly of water, methane, and ammonia. Uranus is unique because it rotates on its side, probably due to a massive collision early in its history. This gives Uranus extreme seasons, with each pole experiencing 42 years of continuous sunlight, followed by 42 years of continuous darkness. Neptune is the windiest planet in the solar system, with wind speeds reaching up to 1,200 miles per hour. This is puzzling because Neptune receives very little energy from the sun, so astronomers aren't sure what drives these incredibly fast winds. Neptune also has the distinction of being the first planet discovered through mathematical prediction rather than observation. Beyond Neptune lies the Kuiper Belt, a region of icy objects left over from the formation of the solar system. The most famous Kuiper Belt object is Pluto, which was reclassified as a dwarf planet in 2006. Pluto is actually part of a binary system with its largest moon, Charon, which is about half the size of Pluto itself. The two objects are tidally locked, so they always show the same face to each other as they orbit their common center of mass. The Kuiper Belt contains thousands of objects, and some of them are quite large. Eris, another dwarf planet, is actually more massive than Pluto. These objects are like frozen time capsules, preserving the conditions that existed in the outer solar system when the planets were forming 4.6 billion years ago. Even farther out is the Oort cloud, a spherical shell of icy objects that surrounds the entire solar system. The Oort cloud is thought to contain trillions of comets, and it extends halfway to the nearest star. When one of these objects is disturbed, perhaps by the gravitational influence of a passing star, it can fall toward the inner solar system and become a visible comet. Some comets take thousands or even millions of years to complete one orbit around the Sunday comet Hale-Bopp, which was visible from Earth in 1997, has an orbital period of about 2,533 years. The famous Halley's Comet returns every 75 to 76 years and has been recorded by human observers for over 2,000 years. Comets are particularly interesting because they contain pristine material from the early solar system, including water, ice, and organic compounds. Some scientists think that comets might have delivered much of Earth's water and perhaps even the building blocks of life when the solar system was young and the planets were still forming. There was a period called the Late Heavy Bombardment, when the inner planets were pelted by asteroids and comets. This bombardment might have been crucial for making Earth habitable. The formation of our solar system itself is an incredible story that we're still piecing together. About 4.6 billion years ago, our region of space was just a vast cloud of gas and dust called a nebula. Something, probably a nearby supernova explosion, caused this nebula to start collapsing under its own gravity. As the nebula collapsed, it began to spin faster and flatten into a disk, with most of the material falling toward the center to form the Sunday. In the outer parts of the disk, small particles of dust began to stick together, gradually building up larger and larger objects through a process called accretion. Close to the sun, where it was hot, only rocky materials could condense, leading to the formation of the terrestrial planets, Mercury, Venus, Earth, and Mars. Farther out, where it was cold enough for water to freeze, the planets could grow much larger by accumulating ice as well as rock. These became the cores of the gas giants Jupiter and Saturn, which grew so massive that they could capture thick atmospheres of hydrogen and helium from the surrounding nebula. The entire process of planet formation probably took about 100 million years, which sounds like a long time, but is actually quite rapid on cosmic timescales. The early solar system was a chaotic place, with planets migrating inward and outward as they interacted gravitationally with each other and with the remaining disk material. Jupiter probably migrated inward toward the Sun before being pulled back outward by Saturn's gravity. This migration might explain why the inner solar system has relatively small planets compared to other star systems we've discovered. Jupiter's inward migration would have scattered much of the material that might otherwise have formed larger planets closer to the Sunday. This brings us to one of the most exciting developments in astronomy over the past few decades: the discovery of exoplanets, planets orbiting other stars. Before 1995, we didn't know if planets were common or rare in the universe. Now we know that planets are incredibly common, with most stars having at least one planet and many having multiple planets. We've now discovered over 5,000 confirmed exoplanets, and the number is growing rapidly. These planets come in an amazing variety of sizes, compositions, and orbital configurations. Some are gas giants larger than Jupiter, orbiting closer to their stars than Mercury orbits the Sunday. Others are super-Earths, rocky planets larger than Earth but smaller than Neptune. Still others are in the habitable zones of their stars, where liquid water could potentially exist on their surfaces. One of the most exciting recent discoveries is the TRAPPIST-1 system, which contains 7 Earth-sized planets orbiting a small, cool star about 40 light-years away. 3 of these planets are in the habitable zone, and they might have the right conditions for liquid water and possibly life. The diversity of exoplanets has revolutionized our understanding of how planetary systems form and evolve. It turns out that our solar system is actually somewhat unusual in having small, rocky planets close to the Sun and large, gas giant planets farther out. Many other star systems have hot Jupiters, massive planets orbiting very close to their stars, or super-Earths, which are common in other systems but don't exist in ours. This diversity raises interesting questions about how common Earth-like planets really are, and what the prospects are for finding life elsewhere in the universe. The fact that planets are so common is encouraging for astrobiology, but we still don't know how often the right conditions come together to allow life to arise and evolve. The search for extraterrestrial life is one of the most active areas of astronomy today. Scientists are looking for life using several different approaches. One is to search for biosignatures in the atmospheres of exoplanets, chemical signs that life processes might be altering the atmospheric composition. On Earth, for example, the presence of both oxygen and methane in the atmosphere is a strong sign of life, because these gases react with each other and would quickly disappear unless they were being constantly replenished by biological processes. The James Webb Space Telescope has already begun this search in earnest, analyzing the atmospheres of distant worlds with unprecedented precision. In 2022, it detected water vapor in the atmosphere of WASP-96b, a gas giant about 1,150 light-years away. While this particular planet is too hot to support life as we know it, the detection proves that we now have the technology to study the chemical compositions of worlds orbiting other stars. But the really exciting targets are the potentially habitable rocky planets. K218b, a sub-Neptune about 124 light-years away, has shown signs of water vapor and possibly even clouds in its atmosphere. Some scientists have even detected hints of dimethyl sulfide, a molecule that on Earth is only produced by living organisms. If confirmed, this would be the first detection of a potential biosignature on an exoplanet. The search isn't limited to oxygen and water vapor. Scientists are looking for what they call biosignature gases, chemicals that would be difficult to explain without biological processes. These include phosphine, which was controversially detected in Venus's atmosphere and sparked debates about possible microbial life floating in the planet's clouds. They're also looking for combinations of gases that would be unstable without constant replenishment, like oxygen and methane together, or oxygen and nitrous oxide. Another approach is to search for technosignatures, signs of intelligent life and technology. This includes traditional SETI, search for extraterrestrial intelligence, programs that listen for radio signals from alien civilizations, as well as newer searches for things like artificial lights on the night side of exoplanets or massive engineering projects that might alter the light output of stars. The most famous technosignature search involves looking for Dyson spheres, hypothetical megastructures that advanced civilizations might build around their stars to capture more energy. While we haven't found any obvious examples, astronomers have discovered several stars with unusual dimming patterns that can't easily be explained by natural phenomena. The most famous is Tabby's star, officially known as KIC 8462852, which shows irregular dimming that some scientists initially thought might be caused by alien megastructures. Scientists are also looking for signs of industrial pollution in exoplanet atmospheres. Just as we can detect natural gases like oxygen and methane, we might be able to detect artificial chemicals like chlorofluorocarbons or nitrogen dioxide that would indicate industrial activity. On Earth, these chemicals have clear signatures that would be detectable from space, and an alien civilization might produce similar pollutants. The search for radio signals continues to evolve as well. The Breakthrough Listen project, funded by tech billionaire Yuri Milner, is conducting the most comprehensive SETI survey ever attempted, scanning millions of stars for artificial radio signals. They're looking not just for intentional messages, but for the kind of radio leakage that our own civilization produces from radar, television broadcasts, and other technologies. One of the most intriguing recent developments is the search for laser signals. If alien civilizations are trying to communicate across interstellar distances, they might use powerful laser pulses rather than radio waves. These optical SETI programs look for brief, intense flashes of light that stand out against the steady background of starlight. Even more speculative are searches for signs of stellar engineering. The concept of a Shkadov thruster, a massive mirror built on one side of a star to create thrust and move entire solar systems, would create detectable asymmetries in starlight. While no confirmed examples have been found, several stars show puzzling properties that have led to speculation about possible artificial origins. The famous Fermi paradox asks why. If the universe is so large and contains so many potentially habitable planets, we haven't found any evidence of extraterrestrial life yet. The numbers are staggering when you think about it. There are an estimated 100 to 400 billion stars in the Milky Way alone, and recent discoveries suggest that most of these stars have planetary systems, even if only a tiny fraction of planets develop life. and only a tiny fraction of those develop intelligent life. There should still be thousands or millions of technological civilizations in our galaxy. Yet despite decades of searching, we found nothing. No radio signals, no obvious signs of stellar engineering, no visits from alien spacecraft. This silence is so profound that it has its own name, the Great Silence. And it's led to dozens of proposed solutions, each more fascinating and sometimes more terrifying than the last. One of the most optimistic explanations is that we simply haven't been looking long enough or in the right ways. Human civilization has only been capable of detecting radio signals for about a century, and we've only been seriously searching for extraterrestrial intelligence for about 60 years. On cosmic timescales, that's less than a blink of an eye. Maybe alien civilizations communicate using technologies we haven't invented yet. Or maybe they're simply not broadcasting in our direction. The Zoo hypothesis suggests that alien civilizations know about us, but are deliberately avoiding contact, perhaps following some kind of galactic non-interference directive like the Prime Directive in Star Trek. According to this idea, Earth might be like a nature preserve, with aliens watching us from a distance, but not interfering with our natural development. A more unsettling possibility is the Great Filter hypothesis, which suggests that there's some extremely difficult step in the evolution of life that prevents most planets from developing intelligent civilizations. This filter could be behind us, meaning that we're among the few life forms to have successfully passed through it. Or it could be ahead of us, meaning that civilizations tend to destroy themselves before they become spacefaring. If the Great Filter is behind us, it might be the origin of life itself, the development of complex cells, the evolution of intelligence, or the transition from single-celled to multicellular organisms. Each of these steps took hundreds of millions or billions of years on Earth and might be far more difficult than we realize. But if the Great Filter is ahead of us, it could be something like nuclear war, environmental collapse, artificial intelligence gone wrong, or some other catastrophe that typically befalls civilizations around our current level of development. This possibility is particularly sobering because it would suggest that our chances of becoming a long-term spacefaring civilization are very low. The Dark Forest hypothesis, popularized by science fiction author Liu Cixin, offers an even more chilling explanation. According to this theory, the universe is like a dark forest where every civilization is a hunter trying to survive. Any civilization that reveals its location by broadcasting signals is quickly destroyed by more advanced civilizations that see all other life as a potential threat. In this scenario, the galaxy might be teeming with life, but everyone is staying quiet to avoid being eliminated. Another possibility is that intelligent civilizations tend to turn inward rather than outward as they develop. Instead of expanding across the galaxy, they might focus on creating virtual worlds, uploading their consciousness to computers, or exploring inner rather than outer space. From the outside, such a civilization might appear to have simply vanished, when in fact, they've transcended physical reality entirely. The concept of a technological singularity suggests that civilizations might undergo such rapid technological change that they become incomprehensible to outside observers. An artificial intelligence explosion might lead to technologies and capabilities so advanced that the civilization becomes invisible to us, operating on scales of time and space that we can't perceive. Some scientists have proposed that we might be living in a computer simulation created by an advanced civilization. which would explain why we don't see evidence of other civilizations. They're either part of the simulation or exist outside it in base reality. This idea, while seemingly far-fetched, has been seriously discussed by philosophers and physicists, including Elon Musk, who has said he believes the odds that we're living in base reality are billions to one against. The rare Earth hypothesis suggests that while simple life might be common in the universe, complex life, like animals and plants, might be extremely rare. On Earth, it took nearly 4 billion years for complex cells to evolve, and most of Earth's history has been dominated by simple, single-celled organisms. The specific conditions that allowed complex life to evolve here, including a large moon to stabilize the planet's rotation, a magnetic field to protect against radiation, and Jupiter to sweep up dangerous asteroids, might be far more unusual than we think. Even more specific factors might be necessary for intelligent life. Earth's location in the galaxy might be crucial, far enough from the galactic center to avoid frequent supernova explosions and gamma-ray bursts, but close enough to have access to the heavy elements created by previous generations of stars. Our solar system's age might also be important, young enough that the sun is still stable, but old enough that previous generations of stars have enriched the galaxy with the elements necessary for rocky planets. The timing of our evolution might also be significant. We evolved during a relatively quiet period in Earth's history, after the late heavy bombardment, but before the sun becomes too bright to support complex life. We appeared after the planet's atmosphere became oxygenated, but before climate change or other factors made the planet uninhabitable. Some scientists have suggested that consciousness itself might be far rarer than we assume. While life might be common, and even intelligence might be reasonably common, the specific type of self-aware consciousness that allows a species to develop science and technology might require an extremely unlikely combination of evolutionary pressures and genetic accidents. The anthropic principle adds another layer to this puzzle. It's possible that the universe contains many regions with different physical laws and constants, and we naturally find ourselves in a region that's compatible with our existence. In most other regions, the physical laws might not allow for the formation of stars, planets, or life, making our observation of a life-friendly universe less surprising than it initially appears. Recent discoveries in astrobiology have both encouraged and complicated our understanding of life's possibilities. The discovery of extremophiles on Earth, organisms that thrive in conditions previously thought to be incompatible with life, has expanded our ideas about where life might exist. We've found bacteria living in temperatures approaching the boiling point of water, in acid that would dissolve metal, in the cooling water of nuclear reactors, and even in the upper atmosphere. These discoveries suggest that life might be possible in environments we previously thought were sterile, like the subsurface oceans of Europa and Enceladus, the methane lakes of Titan, or even the clouds of Venus. But they also raise questions about whether such extreme life would ever evolve into something complex enough to develop technology. The search for life in our own solar system continues to intensify. NASA's Perseverance rover is currently collecting rock samples on Mars that will eventually be returned to Earth for detailed analysis. These samples might contain fossilized microorganisms from Mars's ancient past, when the planet had a thicker atmosphere and liquid water on its surface. The Europa Clipper mission, scheduled to launch in 2024, will study Jupiter's ice-covered moon in unprecedented detail, looking for signs of current biological activity in its subsurface ocean. The mission will use ice-penetrating radar to map the thickness of Europa's ice shell and will analyze particles ejected from the Moon's surface to understand the chemistry of the ocean below. Saturn's moon Enceladus is another prime target for astrobiology. The Cassini spacecraft's discovery of water geysers erupting from the Moon's south pole provided direct access to material from the subsurface ocean. Analysis of these geysers revealed not only water, but also organic compounds and evidence of hydrothermal activity on the ocean floor. Conditions that on Earth support thriving ecosystems. Future missions to Enceladus might include landers that could sample the geyser material directly, or even submersibles that could melt through the ice shell and explore the ocean directly. Such missions would represent humanity's first attempt to explore an alien ocean, potentially answering the question of whether life exists beyond Earth. Titan, with its thick atmosphere and lakes of liquid hydrocarbons, presents a different but equally intriguing possibility for life. While any life on Titan would have to be based on very different chemistry than Earth life, using liquid methane instead of water as a solvent, theoretical studies suggest that such life might be possible. NASA's Dragonfly mission, a nuclear-powered helicopter scheduled to launch in 2027, will explore Titan's surface and atmosphere in detail, looking for signs of prebiotic chemistry or even life itself. But let's zoom out even further and talk about the bigger picture of our place in the cosmos. Our solar system is just one of hundreds of billions of star systems in the Milky Way galaxy, which is itself just one of hundreds of billions of galaxies in the observable universe. The Milky Way is a spiral galaxy about 100,000 light-years across, containing somewhere between 200 billion and 400 billion stars. Our solar system is located about 26,000 light-years from the center of the galaxy, in what's called the Orion Arm, a minor spiral arm between two larger arms. The galaxy is constantly in motion. Our solar system orbits the center of the Milky Way at a speed of about 514,000 miles per hour, taking about 225 million years to complete one orbit. The last time we were in this position in the galaxy, dinosaurs were just starting to evolve on Earth. But even as we orbit the galactic center, the galaxy itself is moving through space. The Milky Way is part of a small group of galaxies called the Local Group, which includes the Andromeda Galaxy, the Triangulum Galaxy, and about 80 smaller galaxies. The entire Local Group is moving toward a massive concentration of galaxies called the Virgo Cluster at a speed of about 1.3 million miles per hour. And here's something that might blow your mind. The Milky Way and Andromeda galaxies are actually moving toward each other and will collide in about 4.5 billion years. This sounds catastrophic, but galaxy collisions are actually quite gentle affairs because galaxies are mostly empty space. Very few stars will actually collide, but the gravitational interactions will completely reshape both galaxies, probably merging them into a single, larger galaxy that astronomers have already nicknamed Milkomeda. When this collision happens, our solar system will probably be thrown into a different part of the merged galaxy, possibly even ejected entirely. But don't worry about it too much, because by that time, the Sun will be nearing the end of its life anyway, and Earth will probably no longer be habitable. The Local Group is itself part of an even larger structure called the Virgo Supercluster, which contains thousands of galaxies spread across about 110 million light-years. And the Virgo Supercluster is just one of millions of superclusters in the observable universe, connected by vast filaments of dark matter in a cosmic web that spans the entire universe. This cosmic web is one of the most amazing discoveries in modern astronomy. When we map the positions of galaxies throughout the universe, we find that they're not randomly distributed. Instead, they form a vast network of filaments and walls surrounding enormous empty voids. The structure looks remarkably like a spider web or the neural networks in a brain, with galaxies concentrated along the filaments and vast empty spaces in between. The cosmic web exists because of dark matter, a mysterious form of matter that makes up about 27% of the universe, but doesn't interact with light or ordinary matter, except through gravity. We can't see dark matter directly, but we can see its gravitational effects on galaxies and galaxy clusters. Dark matter acts as a kind of scaffolding that guides the formation of large-scale structure in the universe. Even more mysterious is dark energy, which makes up about 68% of the universe and is causing the expansion of the universe to accelerate. We don't know what dark energy is, but we know it's there because we can see its effects on distant galaxies. Galaxies that are very far away are moving away from us faster than they should be if the universe were expanding at a constant rate. This means that ordinary matter, the stuff that makes up stars, planets, and everything we can see, accounts for only about 5% of the universe. The other 95% is dark matter and dark energy, which we don't understand at all. We're living in a universe that is almost entirely made up of things we can't see and don't comprehend. The discovery of dark energy has profound implications for the future of the universe. If dark energy continues to dominate, the universe will expand faster and faster, eventually reaching a state where galaxies are so far apart that they can no longer see each other. Stars will eventually burn out. Black holes will evaporate through Hawking radiation, and the universe will end in what cosmologists call the heat death, a state of maximum entropy where no more work can be done. But we're getting ahead of ourselves. Let's talk about how the universe began and how we know what we know about cosmic history. The story starts about 13.8 billion years ago with the Big Bang, the event that created space, time, and all the matter and energy in the universe. The Big Bang wasn't an explosion that happened at a particular point in space. It was the expansion of space itself, starting from a state of infinite density and temperature called a singularity. In the first fraction of a second after the Big Bang, the universe underwent a period of incredibly rapid expansion called cosmic inflation, growing from smaller than a proton to larger than a grapefruit in about 10 circumflex negative 32 seconds. During the first few minutes after the Big Bang, when the universe was hot and dense enough for nuclear reactions to occur, the first atomic nuclei were formed through a process called Big Bang nucleosynthesis. This created hydrogen, helium, and small amounts of lithium, which are still the most abundant elements in the universe today. For the next 380,000 years, the universe was opaque to light because it was filled with a hot plasma of electrons and nuclei. But as the universe expanded and cooled, electrons and nuclei combined to form the first neutral atoms in an event called recombination. This made the universe transparent to light for the first time. And that light is still traveling through space today as the cosmic microwave background radiation. The cosmic microwave background is like a baby picture of the universe, showing us what it looked like when it was only 380,000 years old. This radiation fills the entire universe and has been cooled by cosmic expansion to a temperature of about 2.7 degrees above absolute zero. By studying tiny variations in this background radiation, we can learn about the conditions in the early universe and how the first galaxies and stars formed. After recombination, the universe entered what cosmologists call the Dark Ages, a period when there were no stars or galaxies, just vast clouds of hydrogen and helium, slowly collapsing under their own gravity. The first stars probably formed about 100 to 200 million years after the Big Bang, ending the Dark Ages and beginning the process of cosmic evolution that led to the complex universe we see today. These first stars were very different from the Sunday. They were much larger, more massive, and shorter-lived, because they were made only of hydrogen and helium. When these first-generation stars exploded as supernovas, they created and dispersed the heavier elements like carbon, oxygen, iron, and gold that are essential for the formation of rocky planets and life. It took several generations of stars to enrich the universe with enough heavy elements for planets like Earth to form. Our solar system is relatively young by cosmic standards, forming only about 4.6 billion years ago, when the universe was already about 9 billion years old. We are literally made of stardust, the processed remains of multiple generations of stars that lived and died before our sun was born. The study of stellar evolution has revealed some amazing facts about how stars work and how they die. Small stars like red dwarfs can burn for trillions of years, far longer than the current age of the universe. Medium-sized stars like our sun will burn for about 10 billion years before becoming red giants and then white dwarfs. Massive stars burn much faster and end their lives in spectacular supernova explosions that can outshine entire galaxies. The most massive stars, those with more than about 25 times the mass of the sun, end their lives by collapsing into black holes, objects so dense that their gravity is strong enough to prevent even light from escaping. Black holes are among the most extreme objects in the universe, warping space and time around them in ways that Einstein's theory of general relativity predicted, but that still seem almost magical. These cosmic monsters are so dense that they create regions of space-time from which nothing, not even light, can escape once it crosses the event horizon. The physics of black holes challenges our understanding of reality in profound ways. At the center of every black hole lies a singularity, a point where density becomes infinite and the laws of physics as we know them break down completely. Space and time become so distorted that cause and effect lose their meaning, and the very concept of before and after becomes meaningless. But black holes aren't just theoretical curiosities. They play crucial roles in shaping the universe around them. Stellar mass black holes, formed when massive stars collapse, can have masses ranging from a few times that of our sun to several dozen solar masses. These objects are scattered throughout galaxies, invisible unless they're actively feeding on nearby matter, or have a companion star whose material they're stealing. When matter falls into a black hole, it doesn't just disappear quietly. The process is violent and spectacular, creating some of the most energetic phenomena in the universe. As matter spirals inward, it forms an accretion disk that heats up to millions of degrees, glowing brilliantly in X-rays. The friction and magnetic forces in these disks can accelerate particles to nearly the speed of light. creating jets of material that shoot out from the black hole's poles at relativistic speeds. These jets can extend for thousands of light years, creating structures that dwarf entire galaxies. Some of the most powerful jets are found around supermassive black holes at the centers of galaxies, where they can influence star formation across the entire galaxy by heating up the surrounding gas and preventing it from cooling and collapsing into new stars. Supermassive black holes are among the most mysterious objects in the universe. These giants contain millions or billions of times the mass of our Sun, yet they somehow formed when the universe was very young, less than 1 billion years after the Big Bang. How objects so massive could form so quickly is one of the biggest unsolved puzzles in astrophysics. The supermassive black hole at the center of our own galaxy, Sagittarius A*, has a mass of about 1 million suns and lies about 26,000 light-years away from Earth. We can't see it directly because it's hidden behind dense clouds of gas and dust, but we can observe its gravitational effects on nearby stars. Some of these stars orbit so close to the black hole that they complete an orbit in just 16 years, reaching speeds of up to 7,650 kilometers per second, about 2.5% the speed of light. In 2020, astronomers made the remarkable discovery that one of these stars, called S2, showed exactly the gravitational redshift predicted by Einstein's general relativity as it made its closest approach to the black hole. As the star fell into the black hole's intense gravitational field, its light was stretched to longer, redder wavelengths, providing one of the most precise tests of Einstein's theory ever performed. The Event Horizon Telescope collaboration achieved something that many thought was impossible when they captured the first image of a black hole's event horizon in 2019. The image showed the supermassive black hole at the center of the galaxy M87, surrounded by a glowing ring of hot gas. This ring, called the photon sphere, represents the last stable orbit around the black hole, where light can circle before being pulled in. The image revealed that the black hole was spinning, dragging space-time around with it in a process called frame dragging. This rotation creates an ergosphere, a region outside the event horizon where space-time itself is being dragged around the black hole. In principle, it might be possible to extract energy from a rotating black hole by dropping objects into the ergosphere and having them escape with more energy than they started with, powered by the black hole's rotation. Even more remarkably, in 2022, the Event Horizon Telescope released an image of our own galaxy's supermassive black hole, Sagittarius A*. This image was much more challenging to obtain because the black hole is smaller and its surrounding material is more turbulent, changing on timescales of minutes rather than days. Stephen Hawking's theoretical work revealed that black holes aren't completely black. According to quantum mechanics, they actually emit radiation due to quantum fluctuations near the event horizon. This Hawking radiation is incredibly faint for astronomical black holes, with temperatures far below the cosmic microwave background. But it has profound implications for physics. Hawking radiation leads to a paradox that has puzzled physicists for decades. According to quantum mechanics, information cannot be destroyed. But if a black hole evaporates completely through Hawking radiation, what happens to the information that fell into it? This black hole information paradox is one of the deepest unsolved problems in theoretical physics, sitting at the intersection of quantum mechanics, general relativity, and thermodynamics. Some proposed solutions involve the idea that information might be encoded in the Hawking radiation itself, leaked out through subtle correlations that become apparent only when the black hole has nearly completely evaporated. Others suggest that black holes might not destroy information at all, but instead transfer it to parallel universes or store it in a holographic form on the event horizon. The holographic principle, inspired by black hole physics, suggests that all the information in a volume of space can be encoded on its two-dimensional boundary. This idea has led to the development of the ADS divided by CFT correspondence, a theoretical framework that relates gravity in higher dimensions to quantum field theories in lower dimensions. While highly mathematical, this work has provided new insights into both quantum mechanics and gravity. Black holes also play a central role in some of the most energetic phenomena in the universe. Gamma-ray bursts, the most powerful explosions since the Big Bang, are thought to occur when massive stars collapse into black holes, or when two neutron stars merge to form a black hole. These explosions can release more energy in a few seconds than our sun will produce in its entire 10 billion-year lifetime. Long gamma-ray bursts, lasting from a few seconds to several minutes, are associated with the collapse of very massive stars into black holes. As the star's core collapses, it forms jets of material, moving at nearly the speed of light. When these jets break through the star's surface and blast into space, they create the intense gamma-ray emission that we detect across billions of light years. Short gamma-ray bursts, lasting less than 2 seconds, are created when two neutron stars spiral into each other and merge, forming a black hole. These events, called kilonovae, not only produce gamma-ray bursts, but also create and disperse many of the heaviest elements in the periodic table, including gold, platinum, and uranium. The 2017 detection of gravitational waves from a neutron star merger, followed by observations across the electromagnetic spectrum, opened an entirely new era of multi-messenger astronomy. For the first time, astronomers could study the same cosmic event using both gravitational waves and traditional light-based observations. Gravitational waves themselves represent one of the most remarkable confirmations of Einstein's theories. These ripples in space-time travel at the speed of light and carry information about the most violent events in the universe. The LIGO and Virgo detectors, which are sensitive enough to detect changes in distance smaller than 1/10th the width of a proton, have now detected dozens of black hole mergers and several neutron star events. The black holes detected through gravitational waves have revealed surprises about the population of these objects in the universe. Many of the merging black holes are more massive than expected, suggesting that our understanding of stellar evolution and black hole formation might be incomplete. Some mergers involve black holes with masses that are difficult to explain through conventional stellar evolution. Intermediate mass black holes, with masses between stellar mass and supermassive black holes, remain largely mysterious. While several candidates have been identified, it's unclear how common these objects are, or how they form. They might represent the missing link between stellar mass black holes and the supermassive giants found in galaxy centers. The study of black holes has also led to insights about the nature of space-time itself. Near a black hole, time dilation becomes extreme. If you could watch someone fall into a black hole from a safe distance, you would see them slow down and freeze at the event horizon. Their image red-shifted until it faded away. But from the perspective of the falling person, they would pass through the event horizon in finite time, though they would be torn apart by tidal forces long before reaching the singularity. This stretching effect, called spaghettification, occurs because the gravitational field of a black hole becomes stronger the closer you get to it. Your feet, being closer to the black hole than your head, would experience a stronger gravitational pull, stretching your body until you were torn apart. For a stellar mass black hole, this would happen long before you reached the event horizon. But for a supermassive black hole, you might actually survive crossing the event horizon before being destroyed. The event horizon itself is not a physical surface, but rather a mathematical boundary in space-time. It represents the point of no return, where the escape velocity equals the speed of light. Inside the event horizon, all paths through space-time lead inevitably toward the singularity at the center. But our understanding of what happens inside black holes is limited by our incomplete knowledge of quantum gravity. Most physicists believe that the classical description of black holes breaks down near the singularity, where quantum effects become important. Some theories suggest that quantum mechanics might prevent the formation of true singularities, creating instead exotic objects like gravistars or fuzzballs. The merger of black holes creates some of the most extreme conditions in the universe. When two black holes spiral into each other, they create gravitational waves that carry away energy and angular momentum, causing the orbit to decay. In the final moments before merger, the black holes can orbit each other hundreds of times per second, creating a symphony of gravitational waves that sweep across the universe. The resulting merged black hole is often kicked by the asymmetric emission of gravitational waves, receiving a velocity that can be thousands of kilometers per second. Some of these kicks are so strong that they can eject the merged black hole from its host galaxy entirely, creating a rogue black hole wandering through intergalactic space. Primordial black holes, formed in the early universe rather than from stellar collapse, represent another frontier in black hole physics. These hypothetical objects could have a wide range of masses, from microscopic to stellar, depending on the conditions in the early universe. Some scientists have suggested that primordial black holes might account for some or all of the dark matter in the universe. If primordial black holes exist, the smallest ones would have evaporated long ago through Hawking radiation. But those with masses comparable to asteroids or mountains might still exist today, and their evaporation would create detectable signatures in cosmic rays and gamma rays. The possibility of creating artificial black holes has been seriously studied by physicists. While current technology is nowhere near capable of creating even microscopic black holes, some theories suggest that high-energy particle collisions might create tiny black holes that would evaporate almost instantly. Such events, if they occur, would provide crucial tests of theories about extra dimensions and quantum gravity. Looking toward the future, black holes will play an increasingly important role in astronomy and fundamental physics. The next generation of gravitational wave detectors, including space-based instruments like LISA, will be able to detect black hole mergers across the entire observable universe and study the formation of the first supermassive black holes in the early universe. Advanced computer simulations are revealing new details about black hole physics, from the dynamics of accretion disks to the propagation of gravitational waves. These simulations require some of the most powerful supercomputers in the world and are pushing the boundaries of numerical relativity. The study of black holes continues to challenge our understanding of fundamental physics and may hold the key to developing a theory of quantum gravity that unifies general relativity with quantum mechanics. As we develop more sophisticated tools for studying these extreme objects, we're likely to discover even more surprising and counterintuitive properties of the universe we inhabit. We now know that supermassive black holes, containing millions or billions of times the mass of the Sun, exist at the centers of most galaxies, including our own Milky Way. The black hole at the center of our galaxy, called Sagittarius A*, has a mass of about 4 million suns and is about 26,000 light-years away from Earth. In 2019, astronomers achieved one of the most remarkable feats in the history of science by taking the first image of a black hole's event horizon, the boundary beyond which nothing can escape. The image showed the supermassive black hole at the center of the galaxy M87, surrounded by a glowing ring of hot gas falling into the black hole. Black holes are not just cosmic vacuum cleaners that suck up everything around them. They play important roles in galaxy formation and evolution, regulating star formation through their powerful jets and winds. The energy released by matter falling into supermassive black holes can be so enormous that it affects the entire galaxy, heating up gas and preventing new stars from forming. Some of the most energetic phenomena in the universe are powered by black holes. Quasars, which can outshine thousands of galaxies, are created when supermassive black holes actively feed on surrounding matter. Gamma-ray bursts, the most powerful explosions in the universe since the Big Bang, are thought to be created when massive stars collapse into black holes, or when two neutron stars collide and form a black hole. Neutron stars are another type of extreme stellar remnant, formed when a star with a mass between about 8 and 25 times the mass of the Sun explodes as a supernova. The core of the star collapses to a density so extreme that protons and electrons are crushed together to form neutrons, creating an object about 12 miles across, but containing more mass than the Sunday proper. A teaspoon of neutron star material would weigh about 6 billion tons on Earth. Neutron stars have magnetic fields trillions of times stronger than Earth's, and they spin incredibly fast, sometimes hundreds of times per second. When their magnetic fields are aligned properly, they can produce beams of radiation that sweep across space like lighthouse beams, creating objects called pulsars. Pulsars are incredibly precise cosmic clocks, with some keeping time more accurately than the best atomic clocks on Earth. They were first discovered in 1967 and were initially thought to possibly be signals from extraterrestrial civilizations because of their regular pulsing. The Discovery team even jokingly called them LGMs, for little green men, before they figured out what they really were. In 2017, astronomers made another groundbreaking discovery when they detected gravitational waves from the collision of two neutron stars. Gravitational waves are ripples in space-time itself, predicted by Einstein's general relativity, but only recently detected by incredibly sensitive instruments called LIGO and Virgo. The neutron star collision created gold, platinum, and other heavy elements worth more than the entire global economy, and spread them throughout space. This discovery confirmed that neutron star collisions are one of the primary ways that the heaviest elements in the universe are created and distributed. Gravitational wave astronomy is opening up an entirely new way of studying the universe. Instead of looking at light from distant objects, we can now listen to the vibrations in space-time itself. In addition to neutron star collisions, LIGO and Virgo have detected dozens of black hole mergers, revealing that black hole binaries are much more common than previously thought. The detection of gravitational waves also provided one of the most stringent tests of Einstein's general relativity ever performed. The waves arrived at Earth exactly when and how Einstein's equations predicted they would. Even though they were created by objects billions of light years away and billions of years ago. General relativity continues to be one of the most successful theories in physics, accurately describing everything from the orbit of Mercury around the Sun to the behavior of GPS satellites to the merger of black holes. Billions of light years away. But it's also fundamentally incompatible with quantum mechanics, our other great theory of physics. And this incompatibility is one of the biggest unsolved problems in science. Quantum mechanics describes the behavior of matter and energy at the smallest scales, and it reveals that the universe is far stranger than our everyday experience suggests. At the quantum level, particles can exist in multiple states simultaneously, can be connected in ways that Einstein called spooky action at a distance, and can pop into existence from empty space. The quantum vacuum, what we think of as empty space, is actually a seething sea of virtual particles, constantly appearing and disappearing. These quantum fluctuations are not just theoretical curiosities. They have real, measurable effects on the behavior of atoms and molecules. They might even be responsible for the cosmic inflation that shaped the early universe. Quantum mechanics also tells us that the act of observation fundamentally changes reality. In the famous double-slit experiment, a particle like an electron or photon behaves like a wave when it's not being observed, passing through both slits simultaneously and creating an interference pattern. But when we try to observe which slit it goes through, it behaves like a particle and goes through only one slit. This isn't just a problem with our measurement techniques. According to quantum mechanics, particles don't have definite properties like position and momentum until they're measured. The universe exists in a state of quantum superposition, with all possible outcomes existing simultaneously until something forces it to collapse into a single reality. Some interpretations of quantum mechanics, like the many worlds interpretation, suggest that the universe is constantly splitting into parallel realities, with every possible outcome of every quantum event creating a new branch of the multiverse. According to this view, there are infinite copies of you reading this right now, with slight variations based on different quantum outcomes. Other interpretations suggest that consciousness plays a fundamental role in creating reality, or that the universe is fundamentally information-based rather than matter-based. These ideas sound like science fiction, but they're serious attempts by physicists to understand what quantum mechanics is telling us about the nature of reality. The relationship between quantum mechanics and cosmology is one of the most active areas of research in physics today. Some theories suggest that the universe itself might be a quantum object, existing in a superposition of different possible states. Others propose that our universe is just one bubble in an infinite multiverse, where different regions of space have different physical laws and constants. The idea of a multiverse is supported by some versions of cosmic inflation theory, which suggest that inflation might not have ended everywhere at the same time. In regions where inflation continued, new universes could have been created, each with their own Big Bang and their own set of physical laws. If the multiverse is real, it would have profound implications for our understanding of fine-tuning in physics. Many of the fundamental constants of nature seem to be perfectly adjusted to allow for the existence of stars, planets, and life. If any of these constants were slightly different, the universe might be a very different and much less interesting place. For example, if the strong nuclear force was slightly weaker, atomic nuclei wouldn't be stable, and stars couldn't form. If it were slightly stronger, hydrogen would be rare, and stars would burn out too quickly for life to evolve. If the electromagnetic force were different, atoms couldn't form or would be too unstable to create complex molecules. This apparent fine-tuning has led some people to argue that the universe must have been designed specifically for life. But the multiverse offers an alternative explanation. If there are infinite universes with different physical constants, then some of them will inevitably have the right conditions for life, and those are the only ones where intelligent beings will exist to observe the fine-tuning. The anthropic principle suggests that we shouldn't be surprised to find ourselves in a universe perfectly suited for our existence. Because if it weren't suited for our existence, we wouldn't be here to observe it. It's a bit like being amazed that you won the lottery, when in fact, someone had to win, and you're only amazed because you happen to be the winner. But the search for a deeper understanding of why the universe has the properties it does continues. String theory, one of the leading candidates for a theory of quantum gravity, suggests that the fundamental building blocks of reality are not particles, but tiny vibrating strings. Different vibration patterns of these strings would correspond to different particles and forces. String theory requires extra dimensions beyond the 3 spatial dimensions and 1 time dimension that we experience. These extra dimensions are thought to be curled up so small that we can't perceive them directly, but they might influence the properties of particles and forces in ways that we can detect. One of the most exciting predictions of string theory is that it might provide a way to unify all the fundamental forces of nature, including gravity, into a single framework. This would be the ultimate goal of physics. A theory of everything that could explain all the phenomena in the universe from a single set of principles. But string theory is notoriously difficult to test experimentally because it makes predictions about energy scales that are far beyond what we can achieve with current technology. Some critics argue that string theory isn't really science because it can't be falsified, while supporters argue that it's the most promising path toward a deeper understanding of reality. Alternative approaches to quantum gravity include loop quantum gravity, which suggests that space and time themselves are made up of discrete units, and causal set theory, which proposes that space-time is fundamentally discrete rather than continuous. These theories make different predictions about the nature of reality and might be testable with future experiments. The quest to understand the fundamental nature of reality has led to some of the most sophisticated experiments ever designed. The Large Hadron Collider, the world's largest and most powerful particle accelerator, smashes protons together at energies approaching those that existed just after the Big Bang, creating conditions that allow physicists to study the fundamental particles and forces of nature. The LHC was responsible for the discovery of the Higgs boson in 2012, a particle that gives mass to other particles and completes our current understanding of particle physics called the Standard Model. But the Standard Model is known to be incomplete because it doesn't include gravity and doesn't explain dark matter or dark energy. Future experiments will push even further into the unknown. The proposed International Linear Collider would study the Higgs boson and other particles in much greater detail. Space-based gravitational wave detectors like LISA will be able to detect waves from sources that are invisible to ground-based detectors. New telescopes like the James Webb Space Telescope are already revolutionizing our understanding of the early universe and exoplanets. The James Webb Space Telescope launched in 2021, is the most powerful space telescope ever built. It can see further into space and further back in time than any previous telescope, allowing us to study the first galaxies that formed after the Big Bang and to analyze the atmospheres of exoplanets in unprecedented detail. Some of Webb's first discoveries have already challenged our understanding of cosmic evolution. The telescope has found galaxies that are larger and more mature than expected for their age, suggesting that the early universe was more complex than we thought. It has also detected water vapor and other molecules in the atmospheres of exoplanets, bringing us closer to finding planets that might be suitable for life. The search for life beyond Earth is entering an exciting new phase. In addition to studying exoplanet atmospheres, scientists are developing new techniques to look for biosignatures like oxygen, methane, and even industrial pollutants that might indicate the presence of technological civilizations. The recently launched TESS mission has already discovered thousands of new exoplanets, many of them in the habitable zones of their stars. The upcoming extremely large telescopes, with mirrors 30 to 40 meters across, will be able to directly image Earth-like exoplanets and study their atmospheres in detail, closer to home. Several missions are planned to search for life in our own solar system. NASA's Europa Clipper mission will study Jupiter's moon Europa in detail, looking for signs of life in its subsurface ocean. The Dragonfly mission will send a nuclear-powered helicopter to Saturn's moon Titan to explore its complex organic chemistry. These missions might answer one of the most profound questions in science. Are we alone in the universe? The discovery of life anywhere beyond Earth, even simple microbial life, would be one of the most important scientific discoveries in human history. It would tell us that life is not unique to Earth and might be common throughout the cosmos. But even if we find microbial life elsewhere, the question of intelligent life remains open. The search for extraterrestrial intelligence continues to listen for signals from alien civilizations, using increasingly sophisticated techniques to scan the sky for artificial radio signals, laser pulses, and other signs of technology. Some scientists have proposed that we should also look for more subtle signs of alien engineering, like structures built around stars to capture their energy or chemical pollution in exoplanet atmospheres. If intelligent civilizations are common in the universe, they might have created detectable modifications to their environments. The possibility of contact with an alien civilization raises profound questions about how such an encounter might affect human society. Scientists and philosophers have debated whether contact would be beneficial or dangerous, and whether we should be actively trying to communicate with aliens or keeping quiet to avoid unwanted attention. These questions become more urgent as our own technological capabilities advance. We're on the verge of becoming a spacefaring civilization ourselves, with plans to return to the moon, establish permanent bases on Mars, and eventually explore the outer planets and their moons. The development of reusable rockets by companies like SpaceX has dramatically reduced the cost of getting to space and made ambitious missions more feasible. NASA's Artemis program plans to return humans to the moon by the mid-2022 and establish a permanent lunar base that could serve as a stepping stone to Mars. The first human missions to Mars might happen in the 2032s, and some visionaries like Elon Musk believe that we could establish a self-sustaining colony on Mars within a few decades. This would be humanity's first step toward becoming a multiplanetary species, potentially ensuring our survival even if something catastrophic happens to Earth. But becoming a spacefaring civilization will require solving enormous technical challenges. Long-duration space travel exposes astronauts to dangerous levels of radiation, and we still don't fully understand the long-term health effects. The psychological challenges of isolation and confinement during multi-year missions to Mars are also largely untested. Life support systems for Mars colonies would need to be incredibly reliable, because there would be no possibility of rescue or resupply for years at a time. Colonists would need to manufacture everything they need from local materials, including air, water, food, fuel, and construction materials. The terraforming of Mars, the process of transforming its environment to make it more Earth-like, is a long-term possibility that some scientists are seriously studying. This might involve thickening Mars's atmosphere, warming its climate, and even creating a magnetic field to protect against radiation. But terraforming would take thousands or millions of years and would raise serious ethical questions about our right to modify entire worlds. It might be better to adapt ourselves to alien environments rather than trying to make those environments more like Earth. The prospect of human genetic modification and technological augmentation raises its own set of questions about the future of our species. Some futurists believe that humans will merge with artificial intelligence or upload their consciousness to computers, becoming post-human entities that are barely recognizable as descendants of current humanity. Others believe that we'll use genetic engineering and biotechnology to enhance our physical and mental capabilities, potentially extending human lifespan indefinitely and giving us abilities that we can barely imagine today. These possibilities are no longer pure science fiction. We already have primitive brain-computer interfaces, genetic therapies that can cure some diseases, and artificial intelligence systems that can outperform humans at many tasks. The rate of technological progress is accelerating, and many experts believe that we're approaching a technological singularity where the pace of change becomes too fast for humans to comprehend. Whether these developments will be beneficial or dangerous depends largely on how we choose to develop and deploy them. Technology is a tool that can be used for good or ill, and the choices we make today will determine what kind of future we create for ourselves and for any other intelligent life we might encounter in the universe. The universe is vast, ancient, and full of wonders that we're only beginning to understand. From the quantum foam that underlies reality to the cosmic web that connects galaxies across billions of light years, from the possibility of life on distant exoplanets to the prospect of our own species spreading throughout the cosmos, we live in an age of unprecedented discovery and possibility. Every new observation and experiment reveals new mysteries and raises new questions. The more we learn about the universe, the more we realize how much we don't know. But that's what makes science so exciting. We're explorers in an infinite cosmic ocean, and every wave that reaches our shore brings news of distant and wonderful lands. The journey of discovery that began when our ancestors first looked up at the night sky and wondered what those points of light might be continues today with space telescopes, particle accelerators, and Mars rovers. It will continue tomorrow with missions to Europa and Enceladus, with gravitational wave detectors that can listen to the collision of black holes on the other side of the universe, and with artificial intelligence systems that might help us understand patterns in data that are too complex for human minds to grasp. We are the universe becoming aware of itself, made of atoms forged in the hearts of dying stars, riding a small rock around an average star in an ordinary galaxy among billions of others. Yet somehow, from these humble cosmic materials, consciousness has emerged. Minds capable of contemplating infinity, of asking questions about our origins and our destiny, of reaching beyond our planetary cradle to touch the face of the cosmos itself. In the grand scheme of things, human civilization is incredibly young. If the history of the universe were compressed into a single year, human civilization would have emerged in the last few seconds before midnight on December 31st. We are newcomers to this cosmic story, but we might also be among its most important characters. We might be the first intelligent species in our galaxy, the first to develop science and technology, the first to ask deep questions about the nature of reality. Or we might be one of many, part of a vast community of intelligent beings that we have yet to discover. Either possibility is profound and humbling. If we are alone, then we bear the enormous responsibility of being the universe's only known method of understanding itself. The scientific knowledge we've accumulated, the art and literature we've created, the moral and philosophical insights we've developed, all of this represents the universe coming to know itself through us. If we are not alone, then we are part of something even grander, a cosmic community of intelligence that spans the galaxy and perhaps the universe. The knowledge and wisdom accumulated by alien civilizations over millions or billions of years might dwarf our own achievements, offering us glimpses of truths and possibilities that we can barely imagine. Either way, we are participants in the grandest story ever told. The story of how simple atoms became complex molecules, how molecules became cells, how cells became organisms, how organisms became intelligent, and how intelligence began to understand the cosmos that created it. This story is still being written. Every scientific discovery, every space mission, every moment of wonder as we contemplate the night sky adds new chapters to humanity's cosmic biography. We don't know how the story will end, or even if it will end. But we know that we are privileged to be here now, at this moment in cosmic history when the universe is young enough to still be interesting and old enough to have created beings capable of appreciating its wonders. The facts and discoveries we've discussed tonight represent humanity's current understanding of our cosmic home. But they're just the beginning. The universe still holds countless secrets waiting to be discovered by future generations of explorers, both human and, perhaps, artificial. New telescopes will peer deeper into space and further back in time. New theories will revolutionize our understanding of reality itself. New missions will carry our messages, and perhaps ourselves, to distant worlds. And perhaps someday, maybe sooner than we think, we'll discover that we're not alone in our cosmic journey. We'll make contact with other forms of life, other intelligences that have been asking the same questions we've been asking and reaching toward the same distant stars we've been dreaming of touching. Until then, we continue our lonely but magnificent vigil on this small blue world, studying the cosmos, protecting our planet, and preparing for whatever discoveries and challenges the future might bring. We are the children of the stars, and our destiny is written in the same cosmic processes that created galaxies, planets, and the very atoms of our bodies. As you drift off to sleep tonight, remember that you are part of this incredible cosmic story. You are made of elements forged in stellar furnaces, arranged in patterns so complex they can contemplate their own existence. You are riding through space on a living world that orbits a nuclear furnace in a galaxy of hundreds of billions of stars, in a universe of hundreds of billions of galaxies. And somehow, Against all odds, in this vast and ancient cosmos, you are here. You are conscious. You are aware. You are part of the universe, looking back at itself in wonder. Sweet dreams, fellow cosmic travelers. The universe is vast and strange and beautiful, and you are part of its greatest miracle, the emergence of minds capable of appreciating its infinite mysteries.